Section 5.5 on use substitution, final page, page 3. Evaluate. So we see a definite integral from 0 to 1. We've got a 6 out front, no problem. We know we can pull this out. But we're asked to evaluate the cosine of dt, where we don't just have a t in here. We've got some extra pieces or extra variable parts. So we don't necessarily have a largest exponent, but we also don't just have a cosine of t. So whether you think of u being the innermost function, we're going to let u be all this extra stuff so we can just focus on integrating a cosine of u. So if I let u be pi over 2 times t, then the derivative of u is 1, and I have a du. The derivative of t is 1, but I'm only going to have a pi over 2 multiplied with it, dt. As I notice, I've got a 6 and a dt, but I don't need the 6 and I don't need a pi over 2. So hopefully you remember when you divide by pi over 2, it's really the same thing as multiplying by the reciprocal, where we can cancel terms on the right, but we end up with that pi over 2 on the left. So taking the original problem, first thing I did is went ahead and moved that 6 coefficient out front. Then I took the cosine value I'm integrating over and changed it to u. Now I was keeping it as integrating from 0 to 1 while I had t's in the problem, but now that I've switched to a u, remember I'm changing it to a and b so that I don't forget the actual values I need to be substituting from. So dt, we said, needed to be swapped out with 2 pi over du, and since that 2 pi over du is also a coefficient, I can just bring it out front so that I end up with a 12 pi. The integral of the cosine is the sine, and again, I was saying I'm integrating from a to b, but now that I substitute back where I said u is really pi over 2 times t, now I'm going to put the 0 and the 1. So my f of b minus f of a, which in my case would really be f of 1 minus f of 0, turns out to actually be pretty easy without a calculator. 1 times pi over 2 is just pi over 2. This is asking for the sine of a 90-degree angle, which is 1. Anything times 0 is 0, and the sine of a 0-degree angle is 0. So without a calculator, my exact answer is 12 pi. Second problem. Looks super scary at first, right? We've got all these x's showing up. E to the 25, e to the 81, these sound huge and scary, but this actually breaks down to a pretty basic problem. So I've got x showing up in 2 spots, so I don't have necessarily a largest exponent on the variable, but I do have a piece that I'm considering the inner function. We're thinking of it being inside the square root. So I'm going to start by letting u just be the inside, not the square root of the ln of x, but just the ln of x by itself. I don't know, it's not feeling good, but I'm going to take the derivative of both sides, and because the derivative of the ln of x is 1 over x dx, I really do have an x in the denominator with a dx, so it worked out perfectly. So I'm going to take this original question and I'm going to break it into 2 fractional pieces where my denominator piece, I just went ahead and put a 1 in the exponent. So we're taking 1 over x dx to just be du, and the square root of ln of x is just the square root of u. Now that I'm listing u's, I've gone to my a and b notation. I don't want to write these values. So the square root of u is really u to the 1/2. So I can integrate this one. It's not going to be a natural log, which would be interesting to have a natural log of a natural log, but I'm going to write this as having a negative exponent so that when I add 1 in the disguised form of denominator over denominator, I have 1/2. And so remember, instead of dividing by 1/2, we multiply by the reciprocal. So I have 2 in front of u to the positive 1/2, but I've left it a and b is that reminder to substitute back. So when instead of being u to the 1/2, it's ln of x to the 1/2. I brought that coefficient of 2 out front. I now have my actual a and b values, so I can take f of b minus f of a. And again, at first, this looks pretty messy. But if you remember, we have a law that says, the log of x to the n is n times log of x. So we can just bring that 81 exponent out front, that 25 exponent out front, and because the ln of e equals 1, wherever we would have been left with the ln of e, we have times 1, in both of these cases. But really, we just have the square root of 81, which is 9, the square root of 25, which is 5, and basic subtraction gets us to an answer that looked like we were going to need a calculator, but we didn't. Same will go for this last problem. Now, again, this one looks a little messy, right? We're almost seeing what looks identical, except for it's not quite identical. So if I'm looking for z's to the highest exponent, z is only got an exponent of 1, so it seems like a tie. Z is in the exponent itself, and it doesn't really feel like there's an innermost function, but a good default would to go with whatever function is in the denominator. So we're going to take the ez with the 24 to the z variable, and when I take that derivative, the derivative of e to the z is z, the derivative of 34z is 34, and I've got my dz. If you notice, that was the rest of the problem. So that little extra variable down below in the denominator kind of helped us out. So copying the question, we said the entire numerator could be written as du. The entire denominator could be written as u. And then hopefully you remember this integrates to the natural log, but you could have also written this as u to the -1, and then when you go to add 1 and get that 0, you would know there's a problem. So I've integrated, keeping my a and b as that reminder to substitute back. U is the binomial, and again, this seems kind of messy, but because we're plugging a 1 in to both of these spots, and then a 0 into both of those spots, the math isn't bad. Anything to the 1 power is itself. 34 times 1 is just 34. Anything to the 0 power is 1, and anything times 0 is plus 0, so we didn't really need that. So other than remembering that the natural log of 1 is 0, we had our answer.